Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about the KKT conditions or the first order conditions of the constraint optimization problems, but when we have linear equality constraints and non-negativity constraints. So, those conditions are required to find the stationary solutions, okay, but stationary solutions need not be optimal. So, that is why we require some further conditions to argue whether a stationary point x star is optimal or not. Okay. So, the sufficient conditions for the solution x star of the first order conditions to be minimum for the given formulation are as follows. First, this function z should be strictly convex at x star. So, we have seen what does a strictly convex function means in the previous lectures. The other condition that is required is that this function z should be convex for all x values. So, you can see that there is a slight difference, although here it is required that zx should be strictly convex, but the requirement is that it should be strictly convex at least at x star only. Okay. So, that is the requirement, and here it is saying that it should be convex, but for all x. Okay. And the last requirement is that the feasible region should be convex. Now, this is a new concept that we have not seen until now. So, all of these conditions are the sufficient conditions to ensure that the solution x star of the first order conditions is minimum, that is the stationary point that we find from the first order conditions that we saw in the previous lecture is also the minimum or the optimal solution. Now, this concept that the feasible region is convex is different from a function z being convex. Okay, so let us see what does that mean here. A feasible region is said to be convex if a line segment connecting any two points of the region lies entirely within the region. Okay. So, what it is saying is that if you pick any two points in that region and you join them by a line segment, then the entire line segment should lie within that region. Mathematically, it means as follows: for any point x and y which belongs in this set C, this set C will be said to be convex if for all lambda lying in this interval 0 to 1, we have lambda x plus 1 minus lambda y also lying in this set capital C. So, to denote a point which is lying on the line segment connecting x and y, we have this expression lambda x plus 1 minus lambda y, okay, where lambda is varying between 0 and 1 open interval. So, if this point also lies in this set C, I mean each of these points which lies on this line segment, then the set C is said to be convex, and this has to hold for every pair of points x and y which lies in this set C. So, let us understand this further. This is an example of convex region. Okay. Why? Because you can pick any two pair of points x and y in this region, you connect them by a line segment, and you will find that the entire line segment is lying within this green region. Okay. Whereas, in this case on the right, you are able to find two pair of points x and y, where when you join these 2 points by a line segment, then there are some points like here for example that are not lying in this green region. Okay. So, that is why this region is not convex. Okay. So, this is one example of a convex region. Another example of a convex region would be some region that would be generated by linear constraints. Okay. So, we have discussed this in the discussion of linear programming, that the feasible region is denoted by polyhedron. So, suppose if you have two variables x1 and x2 that are determining the optimization problem, so then we will be getting some polygon as the feasible region. So, suppose this is a feasible region of a linear program. Okay. And we are able to draw in 2 dimensions because we are assuming that the objective function and constraints are varying with 2 decision variables. So, this kind of region which is denoted by polygon is also convex, because you can find any 2 points here x and y suppose, and when you join them here, the whole line segment will be lying in this region. Okay. Another example of a region which may not be convex is something like this suppose. Okay. Now here again you can find 2 points, and when you join them by line segment, so there will be some portions on this line segment which are not lying in this region. Okay. So the minimization of a convex objective function subject to convex feasible region is called the convex optimization problem or convex programming. Okay, so in convex optimization or convex programming, the objective function has to be convex. So we have seen what does a convex function means, and the feasible region has to be also convex, which we have seen in this slide. Okay, so together then this is called a convex optimization. So convex optimization problems usually have very efficient algorithms to solve them. Linear programming is one class of this convex optimization or convex programming. It is the simplest instance of the convex program, but every convex program need not be a linear program. So there are some non-linear programs also which are convex programs. Okay, so this is saying the same thing. Many classes of convex optimization problems have known efficient algorithms. So if we are able to say that our optimization problem is convex, that is the objective function is also convex, the feasible region is also convex, then it is a good news that there are already many efficient algorithms to solve such kind of problems. Okay, so until now we were discussing some theory related to optimization which will be required to solve this user equilibrium problem. So recently we had digressed from the user equilibrium problem to understand these concepts of continuous optimization problems, and now we are coming back again to this user equilibrium problem. So we have not seen the optimization formulation for user equilibrium, so that is what we are going to see here. So this optimization formulation for user equilibrium is called Beckmann's transformation, which is named after the person who had discovered this. So this is called Beckmann's transformation. So let us define some important parameters and variables that are required to describe this optimization problem. Let QRS be the travel demand from origin R to destination S. Okay. Let delta AKRS be 1 if link A is part of the path K connecting OD pair RS, otherwise it is equal to 0. Okay. So these two parameters are given because QRS is the travel demand, that is the number of people who are traveling from origin R to destination S. So this will be an input to the user equilibrium problem. Okay, and similarly this parameter, that whether a particular link is part of a particular path connecting an OD pair RS or not, this information can be derived from the structure of the network that we have. Okay, so we don't need to solve the user equilibrium problem to determine that, that comes from the network structure. So this delta EKRS will also be an input to the user equilibrium problem. So let us define the travel time of link A as a function of flow XA by TXA. Okay. So the travel time functions are given for each link, but since the flow through each link is not known before solving the user equilibrium problem, so therefore the travel time on each link is also not known until you solve the optimization problem. And let FKRS be the flow on path K connecting origin R and destination S. Okay. So this XA is denoting the flow on a link A, and then we have this FKRS which is the flow on path K connecting origin R to destination S. Okay, so XA are useful for the link flows and FKRS are useful for the path flows, but as you can guess they have to be related somehow. I mean, link flows cannot be unrelated to path flows, there has to be some relation, and the way these two are connected is by this parameter delta AKRS that we will be seeing. Okay, so this QRS and delta AKRS are not variables but are given as I mentioned, but XA and FKRS are variables. Okay, because we don't know the link flows and the path flows before solving the user equilibrium problem. The values delta AKRS can be derived from the network structure. So let us see an example to understand that. Suppose this is the graph that we are interested to find the user equilibrium solution. Okay. Suppose you have two OD pairs AD and BD. So some people are interested to go from A to D here and some people are interested to go from B to D here. Okay. Now there are two paths to go from A to D. One is to take link 1 and then go to link 3. The other is to take link 1 and then go to link 4. Similarly, for origin destination pair BD, we have two paths, one to go from 2 to 3 and the other to go from 2 to 4. Okay. So let us now see how we can represent the flow through a link as the combination of the flows of different paths that are passing through that link. Okay. So suppose we are focusing on this link 3 here. So we have this flow through link 3 which is denoted by x3. Now as you can see that this link 3 is part of the first path which is going from A to D, because the first path which is connecting A to D is the one that goes from A to C here and then from C to D. Okay. But this link is not part of the second path which connects A to D, because the second path goes from A to C and then it goes from this lower link, okay, this link 4 here. Similarly, the first path which connects B to D has link 3 part of it, because the first path is going from B to C and then it is taking this top link from C to D. Whereas this second path which is connecting B to D is not having link 3 as part of it, because this second path is going from B to C and then it is taking the lower link here. Okay. So that is why the flow through link 3 should be equal to the sum of the flow that is taking place through the first path connecting A to D plus the sum of the flow that is taking place through the first path connecting B to D. Okay. But now if we have to represent this information for all the links, then we do not want to write such separate expressions for every link flow. So in order to write it in a compact way, we have these variables delta AKRS. So let us now see here. So we have this, the flow through first path connecting A to D times delta 31 AD. So what is this representing? It is saying that this is equal to 1 if link 3 is part of the first path connecting A to D, which is the case. Okay. So that is why this is equal to 1. Okay. Similarly, we have the second term as the flow through the second path connecting A to D times delta 32 AD. Now since the second path which is connecting A to D does not have link 3, because the second path goes from A to C and then it takes this lower link connecting C to D. So that is why this delta 32 AD is equal to 0. Okay. Similarly, we have this third term which is saying F1 BD flow through the first path connecting B to D times delta 31 BD. Okay. So since this link 3 is part of the first path connecting B to D, so that is why this is equal to 1, and then we have this last term which is saying the flow through the second path connecting B to D times delta 32 BD. Now since link 3 is not part of the second path connecting B to D, so this delta is equal to 0. Okay. So therefore we get this whole summation equal to this here. Okay. Okay. So now let us see what is the optimization formulation for user equilibrium, which is called the Beckmann's transformation. So we have this function minimize z, where this is summation over all the links, and the term here is this integral from 0 to xa, and the term inside the integral is this Ta omega dw. Okay. Ta is the travel time function for link A, subject to various constraints that we will be seeing next here. Before we see the constraints, let me just tell you one thing, that this Beckmann's transformation is kind of the first instance of the optimization problem that we saw in this course, and possibly the last one, where there is no intuitive representation for the objective function. Okay. So there is no direct understanding of why this should be the objective function, but then the question will be, then why did Beckmann's transformation is the correct representation for user equilibrium? That is because when we write down the KKT conditions for this optimization problem, those KKT conditions or the first order condition turn out to be exactly equal to the user equilibrium conditions. Okay. So possibly the way this optimization formulation was developed is that there was an understanding of the user equilibrium conditions as the first order conditions, and then in order to get the right optimization formulation that will result into that user equilibrium conditions or the first order conditions, this optimization formulation was developed. And maybe that's the reason that this objective function is not having any intuitive meaning. So let us focus on the constraints. The first set of constraints is that summation fkrs, where the summation is going through all the paths, is equal to qrs, okay, for every OD pair RNS. So it is saying that the sum of the flow on all the paths connecting each OD pair should be equal to the demand for that OD pair RS, okay. So this makes sense. Now note that this QRS is given, okay. So the demand from R2S is given, but how the demands get distributed across different paths connecting R2S, so that we don't know. So that's why FKRS is not known. The second constraint is that the path flows should be non-negative, so we have FKRS greater than or equal to 0 here, okay, for all K and RS. And then we have this constraint that XA is equal to this summation here, where we have three terms, three summations here, one going through all origins, all destinations, and then all paths K, and the term here is FKRS times delta AKRS, okay. So it is saying the flow on each link is the sum of the flows on all the paths going through that link. So this is connecting the link flow to the various path flows. So the example of this we had seen in the previous slide, okay. So since we are using these parameters delta AKRS, that's why it is possible to write down this constraint for every link A, okay. That's the requirement of having these parameters delta AKRS, because we have now compactly written XA is the function of the various path flows, okay. And this delta AKRS is handling the fact whether a particular path K connecting origin R to destination S is containing link A or not, okay. Okay, the objective function, this Zx equal to this summation here, does not have any intuitive, economic or behavioral interpretation, okay. It is a mathematical construct that leads to the solution of user equilibrium conditions, okay. So as I had mentioned, we will be seeing that the first order conditions or the KKT conditions of this Beckmann's transformation are identical to the user equilibrium condition. So if you have this kind of objective function and the constraints that are mentioned, so it just happens that we are able to get the user equilibrium conditions. However, this is the only example of optimization problem where we do not have any intuitive understanding of the objective function. So all the other optimization formulations that we will be seeing will have an intuitive understanding of the objective function. Now note that this Beckmann's transformation is an optimization problem with non-negativity and linear equality constraints, okay. Why is that? So here we have to just keep the focus on constraints. The first set of constraints was that summation FKRS is equal to QRS, that is the sum through all the path flows should be equal to the travel demand on that particular OD pair. So that is a linear constraint because we have summation FKRS equal to QRS. The next set of constraint, FKRS greater than or equal to 0, is again also non-negativity constraint, okay. And the last set of constraint, that is XA equal to those summations FKRS times delta AKRS, this one is not directly clear that why this is fitting into this either the non-negativity or the linear equality constraints. Okay. So remember that this parameter delta AKRS that we have here, this is given because this can be derived from the network structure. Whether a particular link is part of the kth path connecting R to S, that can be known from the network structure. We don't need to solve the user equilibrium formulation for that. So this is given. Then this is a linear function. Okay. So that's why this is also a linear equality constraint. Okay. So that's why all of these constraints that we have are fitting into this framework, because the first set of constraints, summation FKR is equal to QRS, is a linear equality constraint. The second constraint FKRS greater than or equal to 0 is non-negativity constraint, and the last set of constraint, this one, is again linear equality constraints. Okay. So therefore, the first order conditions for Beckmann's transformation can be derived easily. Okay. So in this course I am skipping that part here because it is kind of along the same lines as we had seen the first order condition derivation for this kind of optimization problems where we have non-negativity and linear equality constraints. But if someone is interested, you can refer to this Sheffy's book on urban transportation networks, which I am closely following to see the derivation of how it comes. So we will not be seeing the derivation of how these conditions come, but I will be directly stating these conditions here, that what are the KKT conditions or the first order conditions for Beckmann's transformation. So before we present them here, let us define some important parameters. Let CKRS be the travel time on path K connecting origin R and destination S. Okay. So until now we have not had any notation to define the travel time on path K connecting origin R to destination S. So that's why we have this term CKRS here. So therefore, the first order conditions of Beckmann's transformation are as follows, that is the KKT conditions of the Beckmann's transformation are as follows. So these are the conditions here. If you will closely notice, the last set of conditions here are the normal constraints that we have. The third set here is the flow conservation constraint, that is the sum of the path flows on all the paths that are connecting R to S should be equal to the travel demand QRS, and this is the non-negativity constraint that FKRS should be greater than or equal to 0 for all K, R and S. Okay. But these conditions require some discussion, that what do these mean. Okay. So let us keep focus on that. So we will be focusing on these two conditions here. Now for any path K connecting an OD pair RS, either the path flow FKRS is 0, okay, and if that is the case, automatically this first condition will hold if FKRS is equal to 0. Okay. So then we will be having this thing that by this condition the travel time on this path CKRS must be greater than or equal to the OD specific Lagrange multiplier URS. Okay. This is what it is saying, that CKRS is greater than or equal to URS. So CKRS is the travel time on path A connecting R to S, and it is saying that this is greater than or equal to this OD specific Lagrange multiplier URS. Why we are saying OD specific? Because this U is a function of RS here. Okay. So either FKRS can be equal to 0, and this is what happens, that is we get CKRS is greater than or equal to URS. Or if the path flow is positive, that is this path is getting used, there is some positive flow, and if this FKRS is greater than 0, then this term has to be equal to 0, that is CKRS must be equal to URS by this first condition. Okay. So now you can kind of try to recollect that when we had this user equilibrium condition, we have two set of paths here. One is the set of use paths. Okay. What we had said when we had discussed the definition of user equilibrium, that the travel time on all the use paths is equal and less than or equal to the travel time on all the unused paths. Okay. So use paths have positive flow, so for them the travel time will be equal to URS. Okay. And for all the unused paths, that is the ones which are flow equal to 0, the travel time on those paths must be greater than or equal to this URS. Okay. So now you can kind of guess that this URS is the minimum path travel time between origin R and destination S. Okay. So now this kind of fits into that idea that if we have use paths, that is FKRS is positive, okay, for path K connecting R to S, so then the travel time on this path K connecting R to S must be equal to URS, okay, and this URS is the minimum path travel time between origin R to destination S. And if there is a path K which is having 0 flow and connecting origin R to destination S, so then this travel time on that path CKRS must be greater than or equal to this URS. Okay. So with this we will be ending this lecture here, and we will be continuing in the next class. Thank you.